virtual world, because 1 month of fitness was definitively enough for us now. No, just kidding. But you all know the drill. We better stay home, and that's why we do it online today. A few things changed. One of them is that we will only take 1 hour of your precious time tonight, and that the Astro quiz will not be a live quiz this time. You see the link here, also in yellow. You can see it in the chat. You can see it in the description of the video. You will see the link everywhere. You can just go to this website, answer the 9 questions there is, and then the quiz will be closed in like 45 minutes when your favorite quizmaster Sven will present you the answers to this short quiz. You can win 5 prizes shipped to you at home. So I hope you enjoy these questions. Today we will have 2 guest speakers. One of them is Kathrin Grunthal, and she will tell us exciting things about neutron stars as whistleblowers. So let's stay tuned for that. And shortly after that, you may have already heard the Physics Nobel Prize this year also went again to astronomy, which is very exciting for us as doing science outreach in astronomy. So we will have someone who actually knows a lot of that, and we will have some discussions. And you can always join the chat. You can also ask, you can also reach out to us on Twitter or Instagram. You can send us an email if you were not happy with the explanations today and you just want something written. We will be happy if you say hello to us somewhere. We will be happy if you say hello to us in the chat now, because we really want you to interact with us. Please do that in the chat. We really insist. Mode is there to take care of you, also Anna, and they can help you in various languages to understand what's going on. And they can also relay your questions directly to the speakers, making this event here, hopefully a bit interactive. Also, if you've seen our posters, our announcement, there was a 3rd talk announced today by Jakob Denbrock about navigating into the age of discovery with the help of Arab science and maps. This is unfortunately now postponed to a later date. We hope you understand. And if you just subscribe to any of these social media means, we will keep you updated when we will do this talk. We will also say hello to people from the Science Days, which are digital this time, and they're an awesome platform that help to get all these things that happen online now, because we gotta stay home and make it known to throughout Germany. So if any of you is here because he saw our advertisement on the Science Day webpage, hello, especially to you as well. Yeah, here's again the quiz. It's only 9 questions. You see the link again, which means we really want to get rid of these 5 prizes. And we really want to thank our sponsors for these 5 prizes. It's the SFB 956, is one of the Sonderforschungsbereiche for astronomy that we have here in Germany. And they really have been helpful in the past year and also in this year to keep the event going. And then also recently, the Tai Chi Zentrum in Bonn offered us some courses for free to win just for you. So with that, I give to our favorite moderator, Felix, to guide us through the event.
Thank you very much, Sandra. And also welcome everyone from me, and good evening. Yeah, we had to simplify everything a bit today, so that's why we do everything in English. But maybe you have seen me in the pub. I also know German, so in case you have anything to say in German, it is also fine. I can translate it, and this will be no problem. So yeah, we're not in Fiddlers today, and Fiddlers does not deliver drinks, I think, to your house, but still feel free to grab a beverage of your choice. And I say cheers to everyone. So we will have exciting science for you today. And yeah, let's start with our first speaker, which is Kathrin Grunthal. She started studying physics here at the University of Bonn in 2017, and this summer got her bachelor's degree. with her bachelor's thesis that she did in the Max Planck Institute for Radioastronomy, where I work as well, in the group of Professor Michael Kramer. And her thesis was about the implications of a pulsar's latitudinal beam shape on the predictions of double neutron star merger rates. In case you didn't understand anything just now, this is no problem. We will go in depth on this topic today. And so now I welcome Kathrin. Welcome to the show.
Hi, thank you for having me here.
It's good to have you here. So maybe we start with a bit of the basics of what you did. So maybe you can explain exactly what is a neutron star.
Yeah, I just get my presentation going here. Give me 1 second.
Yeah, I think you have some pretty illustrative slides to show us.
Yeah, that's because I wanted to show the slides. I hope everybody can see them now. So, well, a neutron star is an object that we find in space, and it is not just sitting there. It has to be created in some way. So maybe just go quickly through the creation process of a neutron star. So first we take a massive star. I've grabbed one here for you. And what means massive star? Well, it is a star that has roughly 8 solar masses. So it's 8 times heavier than our sun, or even a bit more heavy. Then at the end of the life of this star, when it explodes, it makes quite a big boom. Then what we are left over with is simply a neutron star. And as you can see here, it has a rough diameter about 10 kilometers, which is, so that everybody can relate to that, the average diameter of a huge city in Germany. And it has almost the same mass as the sun. So maybe you can try to imagine that you try to squeeze the sun into the size of a city in Germany, which is quite dense. So
could be about the same size as Bonn.
Yeah, well, okay, Bonn is not that quite a huge city in Germany, but yeah, just compare it to the size of Bonn. That's correct. So we find that neutron stars are the most compact objects in space, but sadly, as they are dead stars, they are quite difficult to observe for us.
So how do we how can we observe an object that is like so small? And
yeah, well, fortunately, we have something like some subclass of neutron stars. Let's call them neutron star plus, because they have a quite interesting feature. As you can see here, I brought along one of them as a small figure. We have here the neutron star, and what is so interesting about these kind of neutron stars is that the magnetic axis is slightly shifted with respect to the rotational axis. And this is what we call a pulsar, because when this object now rotates, due to this misalignment between these both axes, there is a radio beam. So it is a beam of electromagnetic waves, and that we can easily see through radio telescopes like the ones that is standing in Effelsberg. Now, maybe for all of you, easier to imagine how this looked like. You can relate a pulsar to a huge lighthouse in the sky. So it is quite heavily spinning many times a second, many 100 times a second. And so each time the beam crosses our line of sight, we see like a blob in our radio telescope. And this looks something like this. So as you can see here, this is on the x-axis, the pulse phase. So one turn of the pulsar. And then in the middle, there you see this sharp peak. And this is where we can see the pulsar beam lighting directly towards us.
These are very short, right? These pulses.
Yeah, because as I said, they are quite heavily spinning. So the pulsar that I was working with needed only 144 milliseconds for one turn. So that is quite fast and quite heavily spinning. And so it is also very difficult to just see those individual beams, but with nowadays radio telescopes, we are able to do so.
Okay.
So yeah.
So what are actually like the problems or drawbacks with this?
Yeah. So maybe you can see a little bit of the problem on this picture. So the first problem is that the pulsar beam must point into the direction of the radio telescope, and that is quite a huge problem because the radio telescope only catches a little bit area in the sky, and so every pulsar that is not exactly beaming towards the Earth cannot be seen from the Earth. So we assume, or we know that we only see a vast amount of pulsars out of the pulsar population that is really up there in the sky. And also, due to the fact that our radio telescopes are even more smaller, we only see a cut or a slice of the beam. I try to show this here in this in this figure. We only see like the small slice of the beam where the radio telescope, which is down here, actually is pointing at. That is quite bad because this beam can tell us quite much about the pulsar.
All right. So is there like some way around that? Maybe we observe like some special systems of pulsars?
Yeah, actually, that is all the thing that my talk is about today. When it comes to those systems of double neutron stars, I've brought along another one here. We have a quite interesting effect which helps us to detect axis, and that leads to the wonderful occasion that new parts of the beam become visible. And brought along kind of animation here, how this is working. So we have this pulsar J1906 plus 0476. That is the one that I was working in my bachelor thesis with. So we have here the main pulse and the interpulse. Well, we just distinct them, so it's the one pulse and then the other pulse which comes along after half a turn. And here in this violet, I've shown you the line of sight of the radio telescope. So actually this small line where the radio telescope is pointing at, this is what we see from the beam. And now in each turn that the pulsar makes, we take a snapshot of the pulse. So at the beginning, we see, as you can see here, we see a little bit of the main pulse and quite much of the main pulse, a little bit of the interpulse. This maybe looks like this. As you can see here in the picture, it's a strong main pulse and a small interpulse. Then, due to the precession, the beams slightly move along our line of sight. So now we can see different parts of the beam, and as you can see, which is quite interesting, they are changing in intensity. So the interpulse now becomes stronger and stronger. And now, when we look even longer at this whole thing, we can see only the interpulse, and as you can relate here in this plot, the main pulse is fairly visible, almost vanished, and the interpulse is great to see. And now if we put all this together, we end up with such an intensity map. So as you can see here on the left side, the main pulse, and on the right side, the interpulse. And so the areas that are light here, so they're in yellow, they have great intensity. And to the edges here, it has a quite small intensity. And this is very, very interesting for science, what was detected here.
I think it's kind of written there, but you have to wait like quite a long time until you see this beam crossing the telescope at different points, right?
Yeah, you can see they started the observations in 1998 there, and it took them until 2018 to get this part of the beam. And as you can also see, getting time at telescopes is quite problematic. So there are some areas of the beam that have not been covered in observation because nobody was looking at this, unfortunately, not looking at this pulsar at this time.
I guess we need more radio telescopes then.
Yeah, more radio telescopes. That is very good idea. But what is so interesting about this map is that it's the first of its kind. So this pulsar 1906 is the first one at which this observation was made over at once, this long period of time, as you pointed out, and on the other side with such good radio telescopes that we can really distinctly measure differences in the intensity flux.
There are probably not so many of these double pulsar systems around, right?
Yeah, actually there are like roughly 20 of these that we can see, and interesting for science, even less, or interesting for the science that I was interested in, even less, around about 9 of them we have that are quite interesting for further studies on merging double neutron star systems. And so that's what I want to end with. Whom does that help? So at first point, we have this first intensity chart of a pulsar beam, so we can learn much about the beaming process, about the shape of a pulsar, things that are current questions in nowadays research. And also, this beam shape is of huge interest for simulation of pulsars. So if we would like to do some predictions, for example, as I mentioned, in this double neutron star merge rate, we need to know how many of the pulsars that we can see. And for this, what can we see, is it very important to know what the shape of this beam looks like. So it is very, very interesting what is happening at this point with those systems.
So basically, you can then infer something about these merging events, right? Because eventually all these systems of double neutron stars will merge, right?
Yeah, well, not all of them will merge, but all of those 9 systems that I've mentioned earlier will merge, because those neutron stars, when they form this system, they have to be close enough at each other to begin this in-spiraling process and then this merging process.
Yes, like what you can see in this picture, right? So
yeah, exactly. This is one of the pictures that were produced in order to get a visualization of the process.
This is like the thing with the gravitational waves, right? That we see here.
Yeah, that is exactly. And that is why these pulses are so interesting, because they are not only a field of research for themselves, but they can bring other fields of research together. So they link like the physics of the evolution of these systems, gravitational waves, then this beaming process, and the interior of this neutron star a little bit relates to particle physics. So these are highly interesting objects.
Yeah, I think so too. I think this is very interesting research. And it's really like a pathfinder experiment that you did with this one pulsar. So hopefully we can do more of that in the future.
Yeah, actually they're starting some observation campaigns in order to get a hand on other pulsars exactly the same way. But as you can see, if we start this campaign today, maybe we have to wait 20 years or 30 years, depending on this precession velocity, to get reasonable data that we can work with. So it's a long-term experiment, and that is why it is so important to start now, that we can all get the results from these observations and work with them.
Yeah, astronomers are really known to be patient, or like they at least have to be patient. But developments of instrumentation and getting data can take quite a lot of time.
Yes.
I know that as well. Yeah, this is really cool. So, okay, like Sandra already said, don't be shy in asking questions. We really want to interact with you, and we're there for you also in the YouTube chat. So if you have any questions, post them in German or English. This is no problem. So you can just ask, and we will try to answer that. Yeah, and until there are questions, I have more questions, of course.
That is great.
I mean, you mentioned there are like 20 maybe of those double neutron systems that we could potentially observe, right? So is there any, do you have any idea how many of them could be in our galaxy overall?
Yeah, well, that strongly depends on the beam shape, because when you go through this process step by step, you can think of a universe that is full of these pulsars, and only a slight amount of them is pointing towards us, and that is what we can see. And now if we want to simulate them, so if we want to know from Earth, because from Earth we only know that there are these few systems, and now we have to find a possibility to extrapolate how many are there, then this only or hugely depends on what we can see from them. For example, if we see a pulsar with a small beam, then the probability to see this one is very much lower than if we have a pulsar with a large beam. So in relation, there have to be much more pulsars with small beams than pulsars with large beams. So in order that we can detect from each system one pulsar. So that is why this work on these precessing neutron stars is so important, because what we've seen there is, if you can remember, that this beam shape was highly irregular. So it was not circular. The intensity was not evenly distributed. All things that researchers have assumed over many years. And so that is why this research is so revolutionary, because now we can see that we were working with a little bit the wrong beam shape, and this changed beam shape also changes the numbers that we are extrapolating in the end.
Oh wow, there's a lot of complicated assumptions going in there as well, right? I see.
Yeah.
Actually, I have a question from the chat. It says in those 20 years that the pulsar was observed, there were regular measurements, and they ask how long is one measurement and with which telescope was it done?
Okay, so in this beam shape, there were this one measurement from 1998, and then over a long time they neglected this measurement because it fell a little bit under the table, and then they restarted in 2005 and observed the pulsar until 2009. Then they had a break and observed again the pulsar from 2009. From 2012 to 2018. So the majority of the data points is coming from those two long observational periods from 2005 to 2009 and 2012 to 2018. And actually, they're observing all these different kinds of pulses from with many different radio telescopes all around the world, and this one was observed in the Parkes multibeam survey, but unfortunately I do not know which radio telescopes exactly are
the Parkes telescope in Australia, right?
Yeah. Actually, I've looked it up here in my work, and they also used this Arecibo telescope. Maybe this is the telescope that many of you know from the James Bond movie.
Yes, this one.
Yeah, this one. Yeah.
The very big one. Okay, thank you. I think that we have more questions. Let me check. There's a question about if triple neutron star systems exist. Is this theoretically possible? And what are the consequences? Do you know something about that?
Well, from my heart as a physicist, I would say everything is possible, but actually I'm not that deep in that research, and I've also just started my master in astrophysics, so maybe I can relate this question to somebody else that is here around, or maybe also to Christoph Schürmann, who is speaking after me, who is maybe a little bit more in this topic.
Unfortunately, I myself am not an expert on pulsars, but like from my initial guess, it should be possible that these exist, but they would be exceptionally rare. That's what I would think.
Exactly.
Just statistically speaking.
Yeah, as far as I know, I don't know of any of these systems. And also, as we were talking further a little bit earlier, these systems would be quite rare because of their formation process, and then also they would need one pulsar in them, and then this one pulsar would need to point directly towards the Earth so that we can observe this system, and this is highly unlikely.
I think also like solving the equations for any system with 3 bodies in it is pretty complicated already.
Yeah.
So
you would not want to do this.
Yeah, I mean, people do this, but yeah. I think someone from our team says they have very few stable solutions for any 3-body problem, if they have similar mass, which should be the case for neutron stars. But one could have, for example, like a binary system, like you observed, with a third one that is orbiting at a greater distance. That makes this a bit easier to work. Okay. Yeah, so I think we have no further questions right now, but keep asking them. Maybe we can answer them later. So, and I thank you very much, Kathrin, for being here and sharing with us your exciting research.
Yeah, thanks again for having me here, and I'll stay around until the end, and I'm looking forward to answer more of your questions.
Yeah, thank you. Thank you, Kathrin.
Okay, thanks. Bye.
Okay, we actually have a second topic for you today that Christoph Schürmann will talk about. He also studied physics in Bonn. He's currently working on his PhD thesis in the stellar astrophysics group by Professor Langer at the University of Bonn. And he's also a member of the physics show. Maybe you've seen him there, or you've seen the physics show. I can really recommend it to you. So yeah, welcome, Christoph.
Yeah, hello there. Hello, Internet. And yeah, what are we talking about? We are talking about the recent Nobel Prize. And to give you some faces about this, I brought you some faces, namely this 6 nice guys down here. And I guess you, the audience, you will already know one of them, namely the guy on the upper left, Albert Einstein. He is quite famous. And basically, it's his fault why we have this Nobel Prize this year. Because, yeah,
he is to blame for all this fame for the researchers now.
At first to blame because he in like 100 years ago, he had this funny idea that gravity works different than we thought earlier. Namely, he noticed something interesting about matter, because matter, or let's rather say mass has 2 properties. It can be heavy, so like things falling down, or if you want to lift something, you notice some objects are heavier and some are lighter. And then the second property of matter is inertia. So this means it is difficult to change the movement of an object. A famous example of inertia is if you are driving in your car and going around a curve, you will notice a force pushing you outwards, out of the curve. And the heavier you are, the stronger is this force. And this is called inertia. And yeah, mass has these 2 properties, and these properties, they have exactly the same magnitude. So the heavier an object is, the stronger is inertia. And then Einstein thought, maybe these 2 properties, heaviness and inertia, maybe they are the same. And actually, there is no gravity, no heaviness, and there's only inertia. And that what we perceive as gravity is actually the inert forces of the mass going around the curved space, like the car going around the curve, and you feel the inertia pushing you outwards. Gravity is the inertia due to space-time, due to curved space-time.
So it started with a simple thought, and then it escalated.
It escalated quickly, yes. It escalated so much. He wrote all the stuff down in some equations, and he already noted, well, these equations, they are quite beautiful, but they are also incredibly difficult. And he said, well, I cannot solve them. I guess nobody can solve them. Here's an approximate solution.
So how did that then go on in history? What did people do?
Yeah, so his approximate solution, they were quite successful. So one could show that the gravity we perceive is a consequence of this curved space-time. He could predict that light is deflected by gravity. He could predict that light changes its color due to gravity. And yeah, let's make a small jump in time and go to the next guy in this gallery, to Karl Schwarzschild, the one with a heavy mustache. And back in the time when Einstein developed the theory of gravity, it was only a few years before First World War started. And Karl Schwarzschild was one of these guys who was a bit too much into nation and stuff. And so he went into war as a volunteer and unfortunately died there. But while being bored on the battlegrounds, he actually managed to solve Einstein's equations. The equations Einstein thought to be unsolvable.
That's really interesting. I wouldn't think that someone could do that with war going around them.
Yeah, seems like war is pretty boring. However, I have to say, Schwarzschild didn't find a general solution to Einstein's equations, only one specific solution, namely the solution around a spherical symmetric body, so basically around a star or around a neutron star, around Earth, around a black hole. And yeah, so with this solution, the idea of a black hole was born. And then we are going to make a bigger jump in time, namely to the next two guys. The first one is, I guess, the second one you already know, Stephen Hawking, who died 2 years ago. And together with his colleague, Roger Penrose, he worked, or both of them worked on the mathematics behind the theory of Einstein's theory of gravity. And they discovered a mathematical theorem, the Singularity Theorem, which states that the existence of black holes is a natural consequence of Einstein's equations.
Interesting. I'm wondering if Einstein thought about all this when he developed his theory. All this would follow from that.
Maybe. Unfortunately, we cannot ask him today anymore. Yeah, these two guys, Hawking and Penrose, they also discovered in theory other really cool and interesting properties of black holes. So Hawking postulated this Hawking radiation, that even if black holes can swallow everything, they have a radiation radiating away from them, and so the black hole is losing mass throughout its life. Penrose developed stuff called the Penrose process, which works on rotating black holes. So the idea is that if you throw some matter into the black hole, and if the black hole is already spinning, you can extract energy from the black hole. And with this, in theory, you can power like big engines. So there's a video on YouTube by Kurzgesagt who explained these rotating black holes and the Penrose process, and it's really cool.
Yeah, if it wasn't for that, I could probably not do my research.
On what are you working? Jets?
Yeah, exactly. So I'm working on exactly all these particles that gained a lot of energy from falling into a or close to a black hole, one has to say.
Yeah, nice. So and
all
this
thanks
guy,
to Penrose.
Yeah, all thanks to Penrose and
the guys before him.
And all the guys before him, yes. And this and other discoveries, especially the Singularity Theorem, is one of the reasons why he got the Nobel Prize this year, because he made such big steps in understanding Einstein's theory. I guess if Hawking was still alive, he also would have gotten the Nobel Prize, but sometimes life is not so nice to you.
Yeah, unfortunately, they cannot award post-mortem.
Yeah, so. That's right. And yeah, going on to the next two guys on my slides, you can already see that we have another mustache here. So what I hope you learn from this talk is that if you want to do important research on black holes and general relativity, you should grow a beard. Yeah,
I should probably grow some more beard as well.
Yes, you should. Okay, so Genzel and Gees, the other two Nobel laureates of this year, they are not theorists. They work on the observational side, and they both work on infrared astronomy. So they observe the sky at quite low wavelength. And they both had independently the idea to take their favorite telescope and look at the galactic center. And in astrophysics, processes are always quite slow unless you're working in pulsar observations. And it took some years, and after a while, they saw something very interesting, namely this. You can see this, I guess. So this is a star cluster in the center of our galaxy. And you can see in this image the size of the star cluster. These are 10 light days. So to travel this distance, light needs 10 days. And we are starting in the year 1992. And now I'm going to start this nice movie. And yeah, let's see what we see, what is happening in the star cluster. So now we are zooming in. I guess you already saw that these stars, they are orbiting each other, a common center of gravity. And now I want to focus your attention on this yellow cross in the middle and on the stars when they get close to it. And I'm going to continue the video. And you see that if a star goes very close to this center of gravity, let me go back to the frame, it becomes very fast.
That was really fast.
Again, zoom, there it goes around. Here again. And this is very interesting because this gives a hint that at this yellow cross, that there's a very heavy object. And you can actually calculate the mass of this object by taking the time the star needs to go around it and the physical size of this of the orbit. And in the end, you find that this central object has a mass of about 3 million times the mass of the sun. So 3 million suns, that is quite heavy. And interestingly, it doesn't shine.
That is really heavy. Like, how can such an object just hide from us? Right? It's interesting.
Yeah, what could be so dark, so black, doesn't give away any light? What could it be? Maybe it's a black hole. And yeah, this is the most promising idea, what is down there. Everything else we know about from theory or from observations is giving away radiation. So it has to be a black hole.
It's a pretty heavy, right? So not all black holes are that heavy, right?
Yes, black holes can come in many different masses. Let me show you some other slide about this. So here I've made a small list of black hole masses. And black holes only have one property, namely mass. Everything else disappears because the black hole swallows everything. And if you then weight the black holes, you find that there are like two mass regimes in which the black holes live. The first one, the light black holes from 10 to 100 solar masses, those are the stellar black holes. They are the final product of massive stellar evolution. And on the other hand, they are the supermassive black holes, and they have masses from 1 million solar masses up to 10 billion solar masses. So the black hole in our galaxy, with its 3 million solar masses, it's still light for a supermassive black hole.
This is like incredible that they exist over such many orders of magnitude, right?
Yeah, you have to be aware the scale is not linear, it's logarithmic. So every step is not plus 10, it's times 10.
Yeah. I think we still believe that many processes are similar, right, between these, even with the different masses.
Yes, in both cases we have accretion and jets. You can see this in the two pictures. On the left, for the stellar black holes, it's an illustration. Here, the black hole is stealing matter from a nearby star and pushing parts out as a jet. Here, this blue line going up and down. And the same effect we can observe in supermassive black holes. And I hope the resolution is good enough. This is a galaxy, Messier 87. And from its center, there's a jet coming. It's a bit bluer than the background galaxy. And yeah, it's basically the same process, accretion and jet forming.
So just to finish this off, how many is how do these black holes actually form? Like, how do they come into existence now that we know that they are expected from theory and that we can observe them? How do they come into existence?
Yeah. You can already guess that as we have two different mass regimes, there are two different formation processes, one for stellar black holes, one for supermassive black holes. Unfortunately, the formation process of supermassive black holes is still not understood, so I can't explain it to you. The important thing I almost forgot to mention is the typical, let's say, space where these black holes live. The supermassive black holes are typically found in the center of the galaxy, in the very center. And the stellar black holes are orbiting around with all the other stars, because they are made from the stars, around the rest of the galaxy. But coming back to your questions, how black holes are made, again, supermassive black holes, it's unknown, but stellar black holes, they, as the name suggests, come from stars. So here I've made a little illustration of a life of a star. In the beginning, we have a gas cloud, and this gas cloud basically collapses into the black hole with one very long-lasting intermediate step, namely being a star. The star is actually an intermediate phase from cloud to compact object because it takes so long to radiate all the energy away. And to form black holes, you need very heavy stars. So we already learned that to make neutron stars and pulsars, you need at least a star of 8 solar masses. But to make a black hole, you need 20, 25, or even 30 solar masses. So really, really heavy stars. And because they're so heavy, they are also very bright objects. And throughout the life of the star, they burn in their center all kinds of elements. So at first they take hydrogen, make helium, then they make carbon, and so on and so on and so on, until they reach iron, the element with the largest binding energy. And then this fusion process does not work anymore, and the star becomes unstable and collapses into a neutron star or a black hole. And in this process, it can appear as a supernova. So the little star you see down here is not a star. It was a star, now it's a supernova, forming a neutron star or a black hole. And the funny thing about supernova is that they are basically as bright as a whole galaxy. So this supernova here is not in the foreground, it's in the background within this galaxy, having the same luminosity as all the other stars combined.
Wow, this is really interesting that it's so bright. And then a black hole can form out of this.
Then eventually, if it's heavy enough, a black hole can appear.
Okay. Unfortunately, we have to wrap up now in the interest of time.
Yeah.
But I mean, still, you can ask your questions before we could have a discussion round later today. So please ask the questions. We can also answer them in the live chat. Please just don't forget to interact with us. We really want to talk to you. So thank you very much, Christoph, for giving us some insights about the Nobel Prize winners and their science.
Yeah, thank you for having me.
Yeah, thank you very much. And now we will have the quiz solutions. And so I will hand over to our quiz master, Sven.
Yeah. Hello, can you see me? I hope, yes. Okay, perfect. So yeah, welcome to this quiz. This time in the interest of time, we will make it a bit different because we want to keep the stream in 1 hour. We will just present the solutions. And well, I hope you all sent in your sheets. If you did not, please do that now, because, well, once we present the solutions, we cannot accept any responses anymore, naturally. So yeah, I hope you had fun with this month's quiz, and we will come to the solutions. So first, the category Astro News, which, well, you could probably Google them if you wanted to, but then at least you learned something. So that is nice. So yeah, the first question, the 2020 Nobel Prize in Physics was given to 3 people. If he had been alive, who would almost certainly have been the 4th? Well, I think we have discussed this question, or well, Christoph has discussed this question in quite detail. So who we chose here is Stephen Hawking, because yeah, he really laid groundbreaking work in the theoretical description of black holes. Well, Albert Einstein and Carl Schwarzschild would probably also have been contenders, but they have been, well, Albert Einstein has received the Nobel Prize already, so yeah, it would be kind of unfair. Yeah, so one thing, there are no Nobel Prizes for 4th candidates, so in that case, he might have stolen the one from Penrose. So the question is a bit misleading. In that case, I apologize for that. But well, as far as I can see, you all answered it in the right way. So we can move on to the next one, which is, which famous telecommunication company will soon provide the residents on the moon with mobile internet? And that, I think, so far everyone answered correctly with Nokia. Nokia has been out of the smartphone industry, or almost out of the smartphone industry for a while now, after being one of the pioneers in mobile phones about like 20 years ago. But they are making a comeback, and they won the contract with NASA to install mobile internet 4G on the moon. And well, since NASA has actually a plan to establish a permanent human presence by 2030 on the moon, which I am very curious and excited about. This is actually an important project, because they need the internet for data exchange and, well, for the astronauts who are going to be living there. So this will be installed by, well, it's not entirely certain yet, but one possibility was a little rover, basically Curiosity's little brother. But the more recent plan is that they are going to use a lunar hopper that kind of more looks like this device here on the right, which yeah, will basically use its engine to make short jumps on the moon, land there, deploy a communications tower, and then move on. And the third question, so far we've only brought back material from the moon. Soon that may change, as a sample from ... is currently on the way to Earth. And well, we picked OSIRIS-REx, which is the name of the probe. Most people actually answered with the name of the asteroid, which is Bennu, which also is a correct answer. And here you see actually a little, well, or you don't see it. You should see a little video of the sample being collected. Let's see if that works. Okay, for some reason it doesn't work. I apologize for that. But okay. Yeah. The mission plan for this probe was to first observe this asteroid, which it did for 2 years. It just circled this asteroid at a distance of 5 kilometers, sorry, to then finally collect the probe. And then a little mishap happened. The original plan was then to spin the asteroid, to spin the probe and measure the weight of the container by the inertia that is registered from the, well, basically by the centrifugal force. Unfortunately, on the camera, they saw that this container could not close because they had collected too much sample material. Problem, because due to that, the samples started leaking out into space, so they skipped that part of the mission, and the lander is returning to Earth directly, and we don't know how much sample it has collected. The plan was for 60 grams, but it's probably going to be more. And finally, the GIF is working, so you actually see the sample being collected from this asteroid, which is quite fascinating, I think. Okay, we're coming to the last part, which is Pictionary, where we, well, had our very talented astronomers draw you pictures, and you should guess what they were. And we have one problem. 2 of the pictures were too good. They were too easy to guess, and you all guessed them correctly. So here you see a radio telescope, more precisely the radio telescope in Effelsberg. It's quite close to here. It's maintained by the Max Planck Institute for Radioastronomy, our neighbors, or well, many of our members are also members of this institute. And yeah, it's a really, really fascinating piece of technology, and well, definitely the most important telescope we have here in Germany, I would say. Then we come to the second picture, which, as also most of you have guessed correctly or figured out correctly, is a sketch of Alfred Nobel, or of the front side of the Nobel Prize medal. Yeah, Alfred Nobel was a man of many talents and many patents. One of his patents was, or a few of his patents were also in weapons technology, which, well, basically he wanted his legacy to be something else. So he founded this Nobel Prize, which is given to people that have significantly contributed to the, yeah, basically to the advance of humankind. And well, this is what we all know him for today. So he definitely changed his legacy there. Yeah, and we are coming to the last picture, which goes more in the direction of Pictionary, because it was quite hard to determine what it was. So the intended answer was the Death Star. We requested the picture like this, and you see it looks kind of similar, but also a valid answer would be Pokeball, because yeah, you see that it also looks kind of similar. Yeah, then we come to the movie posters, where we basically show you a very, very minimalist picture of a movie, or very, very minimalist interpretation of a movie poster. So the first one is from the movie Apollo 13, which is basically about the Apollo 13 mission. So the failed lunar mission that, well, they had a problem when they stirred an oxygen tank, it exploded. And due to an enormous amount of ingenuity and genius, both from the sides of the astronauts and NASA, they actually managed to return this home, and all astronauts survived. But they were unable to land on the moon. And this movie is about that incident. It's a very good movie. I can highly recommend it. Then this movie picture is of the movie Arrival, which deals with some aliens coming to Earth and establishing first contact. Also a very interesting movie. And the third one, of a little sprout on something red, is of the movie The Martian, which deals with an astronaut being stranded on Mars and having to survive for a long amount of time, just relying on his wits and on some potatoes that he grows. Also a very, very nice movie, and I can highly recommend it. So yeah, that was the quiz for this month. We have a few prizes for you. You can win them by answering more than half of the questions correct, and then just be lucky enough to be selected among the 5 winners. And yeah, we hope you posted a valid email address, because that's how we are going to contact you if you won a prize. Please mind that we cannot ship prizes outside of Germany due to shipping costs. What can you win today? You can win a little booklet by the Euclid Consortium for personal notes, an Astronomy on Tap mug, the book An Astronaut's Guide to Life on Earth, some vouchers for Tai Chi in Bonn, and a little metal figurine of a Death Star that you will have to assemble yourself, but it's a very, very nice piece of equipment or of decoration. And yeah, with this, I wish you good luck, and I return back to our hosts.
So that would be me, I guess. So one of the hosts. And I just wrapped this up in the last few minutes that we have. That was an awesome event. Thank you, Kathrin. Thank you, Christoph, for these awesome talks. I think it was quite fitting that we talked about pulsars and the Nobel Prize, which were about the black holes, because these are the end stages of stars, so like the death of the star. And since it's almost Halloween, that was like, yeah, the spookiness of this event. I hope you had a lot of fun. I had a lot of fun. I also learned something. And we are back in the 24th of November, 7 p.m. here live on YouTube from your couch, Astronomy on Tap Bonn live. We will most probably talk about what the universe looks in different directions. So I give you a spoiler, it should look like the same approximately in all the directions, but there's a little bit of difference, and we can learn a lot about that from this little bit of difference. We will have another quiz that we will advertise to you beforehand. Again, lots of prizes to win, so just participate, and then we will tell you the answers to the quiz during our live 1 hour. And as you may notice, we always sneak in some of the news that happened in the past month about astronomy, that you stay tuned to what is actually happening. So for now, if you had not had enough in this 1 hour of Astronomy on Tap, and you have more questions, or you just want other people asking questions and you just listen a bit more, we want to invite you to our Zoom discussion. You can find the Zoom link under the link that I've shown here. It will also be posted in the chat. As far as I know, you don't need a Zoom client. You don't need to download the application to actually view it. At least it works if you have a browser like Firefox. And you can talk to the speakers. You can ask your questions. Your favorite moderator will be there, the favorite quiz master as well, and lots of people from the infamous AOT background, because there's many more. We have a lot of people. We have people who manage the quiz. We have people who manage all the technicalities. Thanks, Laila. Thanks, Mo. Thanks, Anne, at this point. And also lots of more people who help us with doing the graphics, advertisement, just collecting these awesome quiz prizes. And we hope you had fun. I had fun. Hope to see you next month. And with that, we are off for now in the YouTube, and we expect you to maybe join in the Zoom just now.